Welcome back, everybody. It's good to be back with you, virtually that is. We're in the middle of the COVID-19 pandemic right now, and so all of the remaining lessons for our 641 Advanced Soil Mechanics class will be uploaded to YouTube for you guys to enjoy. So that will be good news for you guys in the sense that you'll be able to come back and watch these for years to come while you're out in your profession. So, and it's good for me because it helps encourage me to actually record the lessons and get them up there for everyone to use and to enjoy. So, I've been excited to give you guys this lesson all semester long. And that's because we're talking about calculating the magnitude of settlement today. In advanced soil mechanics, with the limited time and topics that I can choose to discuss in the time that I have, I'm not going to discuss time of settlement, which is a very important topic, and there's plenty of references out there that you can find that will give you more information on that. But instead, I want to focus today on computing the magnitude of the settlement, and I want to introduce you in particular to a lesser known method for computing settlements, but it's one that I was introduced to in my graduate studies, and I really, really liked it. And I want to introduce it to you guys as well in case you haven't come across it yet, because I think you'll find it could be very useful in your career and in your own analysis as a geotechnical engineer. So let's go ahead and just dive right in and do a review of computing the magnitude of settlement. And a lot of this material is pulled directly from my elementary soil mechanics class, which the lessons are also uploaded onto my Office Hours YouTube channel. And that's my 341 class. So for those of you who are in my 641 class right now, these slides will look familiar to you. They should. It's just a review, but this is intended to just refresh your memory because we're going to talk about a couple new things. So when we talk about settlement basically is this idea of the soil behaves somewhat like a spring, and the soil, the spring, has a load on it, and if we change that load, either take load away or add new load to it, that spring is going to deform. It's either going to elongate if we take load away, or it's going to compress if we add more load. And if we think about the soil in the sense of lots of sublayers of soil, think of it as lots of little springs stacked on top of one another. So if we can calculate the deformation in each little spring and sum them up over the whole depth of the soil profile, we can come up with an estimate of the total settlement that occurs in that soil. So when we talk about settlement, you'll recall that there are three quote-unquote types of settlement that we need to consider, and each one has a different mechanism, and that's why we need to separate them or evaluate them differently. So the first is what we call elastic settlement or immediate settlement, and this is due to the elastic distortion of the soil particles. So quite literally, the spring example that I just gave. The soil behaves elastically. If I load it up, the soil particles compress. If I remove a load, the soil particles decompress and elongate. And so this type of settlement occurs immediately, just like if you load or unload a spring, deformation occurs immediately. This type of settlement is the primary cause of settlement for coarse-grained soils. The second type of settlement is called primary consolidation settlement, often represented with an S sub C. And this is caused by a decrease in the void ratio as water is expelled from the soil. And so this type of settlement occurs over a long period of time generally. It's dependent upon the soil's hydraulic conductivity, or how quickly it can move water through it, as well as the thickness of the soil layer. And so it may require months to even years to occur in a particular soil layer, depending on the properties of that soil. This is the primary cause of settlement for fine-grained soils. The third type of settlement is secondary consolidation settlement, represented as an S sub S. And this is due to long-term distortion of the soil due to decomposition of the soil, chemical changes in the soil, or plastic creep. And so the interesting thing about secondary consolidation is it is always present, and there's really nothing we can do to eliminate it or make it go away. All we can do is reduce its effects. Its effects are particularly significant for soils that have a high liquid limit and a high water content, or soils that are organic in nature, because organic soils tend to decompose, and so that decomposition causes the whole structure of the soil to change and will cause it to settle. So these are our three types of settlement: elastic settlement, primary consolidation settlement, and secondary consolidation settlement. So we're going to blast through each of these just as a review. Well, actually, I'm not going to talk about the elastic settlement in this lesson. If you're interested in that, go back and find my elastic and consolidation lesson in the 341 class. What I want to do is I want to dive straight into primary consolidation and do a review of that. So in the primary consolidation test, basically what we do is if I'm in the lab and I have a block of soil that I retrieve from the field somehow, I'm going to carve out from that soil a little, I'm going to carve out a little disc, a little, almost looks like a hockey puck. And I don't actually carve it out. What I do actually is there's a steel ring. If we're using a one-dimensional consolidometer, and that steel ring has a little sharp cutting edge to it on the inside. And so I'm going to take that ring and I'm going to push it down on top of my soil block. And I'm going to push it down until soil fills the ring. And then once I have soil in the ring, I can take it and load it into a consolidation test. So the consolidation test just applies a piston to the top of the soil. If I take a cross section of what that ring looks like, here's the ring, here and here. So we just cut the ring in half basically. And here's the soil in the middle of the ring. We cut that in half. And we place some porous stones on the top and the bottom of that ring with the soil in it. And those stones are just intended to keep the soil inside the ring, but still allow water to drain in and out without allowing the soil to drain in or out. And what we're going to do is, once we get those stones on there, we place that whole scenario, or we place that whole setup inside of a little tub that then we're going to saturate with water. And then we place our piston over the top of the whole thing with a load. And then we control that load. And on top of that piston, we have a little LVDT, which just measures the strain or the displacement that's occurring. And it measures it very, very accurately. And so we can watch how, as the soil deforms, as we change the load on our soil sample. So what we measure with that odometer is or that LVDT, is the deformation with time once we apply a load. So we can apply our load, and as time passes, we watch as the soil slowly starts to compress. And there's a point where it accelerates and it speeds up and it compresses at a constant rate, which is this rate right here, for a certain amount of time. But then that rate starts to change right in here. And that's when we're nearing the end of primary consolidation. That would be stage 2 according to this plot. Stage 1, of course, is just the initial compression or the seeding load. And then once that rate of deformation changes, it becomes constant again, but it is a much lower rate. And so down here, that rate would correspond to our secondary consolidation. So that's how a consolidation test, or an odometer test, sometimes what it's called, is performed in the laboratory. Now, if we represent the soil as simply as a phase diagram, we can show it right here. We have the height of the voids and we have the height of the solids. And the voids are completely filled with water. There's no air in the soil because we've saturated the soil. And as the soil deforms with load, what's really happening is the height of the voids is changing. We're squeezing more and more water out of the void space. And so the total height of the soil is changing, but the height of the solids is constant. The height of the solids cannot change because the solids are just solid mass that are incompressible. And so that height of the solids will never change in a phase diagram. What changes is the void space, or the height of the voids. So as that sample consolidates and compresses, the height of that voids is getting smaller and smaller. Now, we often represent this change in height as in terms of change of the void ratio. Now, you'll recall that the void ratio is equal to the volume of the voids divided by the volume of the solids. And so as that volume of the voids decreases, and by the way, that's also approximately equal to the height of the voids divided by the height of the solids in the one-dimensional consolidation test. Okay, so that's how we're getting our void ratio here. Now, as we plot then this void ratio with what happens with the load that we're applying to it, if we plot that load on a log scale, we get a curve that looks like this bad boy, where we get a very gradual change in void ratio at lower stresses, but eventually we reach a point where that change in void ratio accelerates, and now we have a much steeper rate of change of void ratio with change of stress. So this curve, if you'll recall, is what we call a consolidation curve. And we can plot then, in a consolidation curve is the change in void ratio with the change in effective stress on that soil. Now, here's the challenge though. Void ratio isn't something that we actually measure in the lab. It's something that we calculate. And so this is a tricky part for students because we're plotting something that we're not actually measuring, we're calculating. So I've given you guys some steps right here to help you get to something that you can measure, which is the change in the height of the voids. That change in the height of the voids is simply the change in the odometer reading. And the height of the solids, this is something that you calculate from your phase diagram. stuff that we learned in elementary soil mechanics and the weight of the solids as well. But all of this information will be helpful to you so you can create your traditional Terzaghi consolidation curves. Now, a lot of other professionals prefer, instead of plotting void ratio, they like to plot their consolidation curves in terms of strain. And strain, you'll recall, is just the change in height divided by the original height. And believe it or not, the shape of the curve is still the same thing because strain is directly proportional to void ratio. Or change in strain is, I should say, strain is directly proportional to change in void ratio. So a lot of engineers prefer to plot their consolidation curves as a strain instead of a void ratio, just because it's easier. You don't have to do a calculation, and you're certainly welcome to do that. The only thing you need to be aware of is if you take the slopes of these curves, it's no longer C sub r, it's what we call C sub r prime. And C sub c is now C sub c prime, where C sub c prime is going to equal 1 over 1 plus E naught times C sub c, and C sub r is going to equal 1 over 1 plus E naught times C sub r. That's all you need to know to go back and forth between these two. I personally like to plot my curves in terms of strain instead of void ratio, but tomato, tomato, you get to plot your curves however you guys want to. But let's go back to void ratio space, just because this is the original method that Terzaghi himself introduced to everybody many years ago. Let's talk a little bit about why the curve is shaped as it is and why the curve has this initial low change in void ratio with low stresses, but eventually gets to this point where we have a large change in the void ratio. Now, all of this is because the soil itself, the fine-grained soil, it has memory, which is pretty remarkable. The soil fabric remembers the largest stress that it was ever exposed to in its past. And that doesn't matter if the stress was thousands of years ago. The fabric remembers what that stress is. And so that stress, that largest stress that it was exposed to in the past, is what we call sigma prime P, or sometimes sigma prime C. That's called the pre-consolidation stressor, or the pre-consolidation pressure, or the pre-consolidation stress. It's the maximum past effective stress that soil has ever felt. And it marks then the boundary between this low change in void ratio and this high change in void ratio. And lots of times when we do a consolidation test, let me go back to this plot right here. We'll load up our consolidation curve. Load it up, load it up. We reach the pre-consolidation stress of the soil, and the slope of that curve will change. And now, every time we increase the stress, that stress becomes the largest stress the soil has ever felt. So, but until we reach a certain point, if we ever decide to back the stress off, and instead of increasing it, we decrease it, that curve will follow a shape that looks like this. We call that the rebound curve. And interestingly, the slope of that line theoretically should be the same as the slope of the line up here. And this stress now has become our pre-consolidation stress for that soil sample. And that's why we're seeing this plot down here. Okay, that's what that's representing. Now, let's look closer at this pre-consolidation stress. We would say that if you're in this range right here, if the stresses that the soil is feeling is less than the pre-consolidation stress, then the soil is what we call over-consolidated. It's almost like tempered soil. The soil has felt greater stress in its past. the current effective stress is less than the pre-consolidation stress. Now, if your soil is in this region right here, then it's on the virgin compression line, and we would say then that the stress that the soil is currently feeling is the largest stress it has ever felt in its existence. And so that is what we call normally consolidated. So there's two types of soils. There's normally consolidated soil and there's over-consolidated soil. Now it's convenient for us to calculate a simple ratio. The ratio of the soil's pre-consolidation stress to its current effective stress. Now, the pre-consolidation stress is always going to be greater than or equal to the effective stress that the soil is feeling. Therefore, the over-consolidation ratio is always going to be greater than or equal to 1. It's never going to be less than 1. Now, if this ratio is what we call the over-consolidation ratio, or the OCR. So if the pre-consolidation stress is larger than the current effective stress, then that OCR, that ratio, is going to be greater than 1. So if OCR is greater than 1, the soil is over-consolidated. If the pre-consolidation stress is equal to the current effective stress, then OCR is going to be approximately equal to 1, and the soil becomes normally consolidated. So let's come down and look at our plot of consolidation here. And there's a couple points here. We have point A, we have point B right there, we have point C right there, we have point D right here, and we have point E right here. These are just points on our consolidation curve. Now, if I want to look at what's going on between points A and B, this portion of the curve right here. That portion of the curve, the soil is over-consolidated because our stresses are less than the pre-consolidation stress. Therefore, the change in void ratio, the change with void ratio, the change in stress is very small, so limited settlements generally occur. Now, from point B to point C, you'll see that there's a transition that's happening. That curve is starting to curve a little bit. So that's the transition from over-consolidated to normal consolidated. Now, if we go from point C down to point D, you can see that the slope of that line is very much changed, and it's steeper than in recompression. And this is where the soil is normally consolidated. It's on the virgin compression line. We tend to see lots of settlement with changes in loading, and settlements generally take much longer to occur than they do when the soil is over-consolidated. Now, if for whatever reason we were to back the stresses off or unload the soil, then we're back in recompression. And we're in rebound, and that's what we call the rebound curve. And the soil is over-consolidated again. And it should have about the same slope as lines A, B up here. So, you know, it would be really nice if every consolidation curve looked as clean as this one. The reality is they don't. In fact, most consolidation curves from soils that you obtain from the field, they look more like this. And it's really difficult to find that pre-consolidation stress. I mean, does that break in the curve happen here? Does it happen here? Does it happen here? It can be really, really challenging to find that. And that smashed curve appearance occurs because the soil fabric is disturbed during sampling, during retrieval from the ground and transportation back to the lab, and installation into the consolidometer and testing. And so all of that mumbo jumbo that you're doing to the soil is causing disturbance in the soil fabric, and that disturbance in the soil fabric is going to flatten your consolidation curve. So some previous researchers have developed some methods to try to help us to find that pre-consolidation stress. One of those was Casagrande. Arthur Casagrande developed the graphical procedure for finding pre-consolidation stress. Here are the steps for doing that. The first step, he said, is find the point of maximum curvature, the maximum curviness on our consolidation curve, which would be about right here on this plot. That's where the curve seems to curve the most. And a part of step 1 then is to draw a line tangent to that point of maximum curviness. So that's line 1 right there. Step 2 is to draw a horizontal line through that point of maximum curviness, a horizontal line. So now we have this angle right here between the two lines that we drew. Okay. Step 3 is to draw a line right in between there. Well, that wasn't very good. Right in between there, we're going to bisect that angle. Okay. That's step number 3. Then step number 4 is to come way down here where the soil is normally consolidated and use your ruler to find the slope that fits that normally consolidated line, and then extend that slope as far up here as you can. Now, Casagrande says where that extension intersects that bisector line, the stress that corresponds to that intersection point is approximately your pre-consolidation stress. So that's how Casagrande said you can find your pre-consolidation stress. Now, I've done hundreds of these in my career, and it's not always neat, and it's not always accurate, and it's messy and a little time consuming. I mean, you can get to the point where you can pound those things out in under a minute, but later in this lesson I'm going to show you a different way, which is a lot less sensitive to disturbance in the soil fabric. So let's get in and let's talk about settlement itself. Just like you've learned in other classes like mechanics of materials, we can compute deformation in any material if we know the strain of the material and its original thickness. You'll recall that strain in a material, well, let's just say deformation is simply equal to the strain of a material times its original thickness. And of course, strain is equal to the stress divided by the modulus of that material times its original thickness. And this is where we always get the famous equation PL over AE when we talk about deformation of a steel bar or any of deformation of a wood beam or those kinds of things. That's deformation. Okay, now soil, we're going to follow the same rules. The settlement is like deformation of the soil, and that's going to be equal to the strain in the soil times the thickness of the soil layer. So let's look at a single saturated soil layer. The thickness of the layer, or the height of it, is equal to H. And the primary consolidation causes a change in the soil of delta H. That's in the volume of the voids, or the height of the voids. So if we look at a unit phase diagram where we have the volume of the voids and the volume of the solids, and we call it the unit phase diagram because the volume of the solids is equal to 1. That means the volume of the voids is equal to E naught, the void ratio, because you remember volume of voids over volume of solids equals void ratio. And if volume of solids equals 1, then that's simply going to equal the void ratio. So that's why we say with the unit phase diagram, the volume of the voids is just equal to the void ratio. And the total volume of the soil is equal to 1 plus the void ratio. So that change in volume is equal to the change in the void ratio. So the strain is equal to the change in height divided by the original height. But because this is a one-dimensional consolidation test, if I just tack on an area, the cross-sectional area of that soil would give me, of course, the volume. That's the change in volume. And down here, if I tack on an area to that height, that's going to give me the original volume. So the change in volume divided by the original volume is the same thing. And notice how the cross-sectional area doesn't change because it's constrained by my rings. So the change in volume divided by the original volume, or the volumetric strain of that soil, is the same as just the deformational strain, the change in height divided by the original height. So we're going to call this equation up here equation 1. And down here, the change in void ratio divided by the 1 plus the original void ratio, this is the same as the change in height divided by the original height of the soil. This is what we're going to call equation 2. If we combine these equations and plug that strain from equation 2 into equation 1, we end up with this governing equation down, this governing equation down here at the bottom, where the settlement for the layer is equal to the change in the void ratio divided by 1 plus the original void ratio times the thickness or the height of that soil layer. So now all we need to do is come up with the change in void ratio. Well, how do we get that? Easy. We use the consolidation curve. If the consolidation curve tells us if we can predict what the change in stress is in our soil layer, then we can predict what the change in void ratio is going to be. So there's 3 possible cases that we could have. For instance, if my original stress corresponded to this right here, and my final stress, let's go over here. If my original stress was right here, and then I have some induced stress, and that induced stress takes me all the way down here on the virgin compression line, I was already normally consolidated because my initial stress was equal to my pre-consolidation stress. So I was already normally consolidated. Now with my induced stress, I'm just further down the compression line, and that my new pre-consolidation stress will be equal to this guy right here. If that's what I have, then I have what I call case 1. The soil is normally consolidated and it stays normally consolidated. If that's the case, I compute my change in void ratio using this equation right here, where C sub C is the slope of that normally consolidated line. Okay. It's the slope of the line. C sub C is just the change in void ratio divided by the change in the log of stress. So you got to remember that your x-axis, the stress, is in log units, not in linear units. So this equation here is how we get our change in void ratio, and if I plug that into the equation we derived on the previous slide, this is how we would compute the settlement for that soil layer. Now, case number 2 would be if my effective stress in my soil was up on the over-consolidated portion of the consolidation curve, and my induced stress still kept me on that over-consolidated portion of the curve. I'm still less than my pre-consolidation stress. My induced stress was not enough to get me past that stress. So if that's the case, then I need to use a different slope. I need to use the slope of the recompression line that's going to be this slope right here. That's going to be C sub r. So you'll see this equation from case 1 is very similar to the equation from case 2. The only difference is I'm using C sub r instead of C sub c because I'm on a different slope of the curve. And that's how we would compute settlement for that. Now, the third case is an interesting case. The third case is, what if my soil initially is over-consolidated? My effective stress is less than my pre-consolidation stress. But after I apply my induced stress to the soil, it's enough to get me past the pre-consolidation stress such that now I'm over here on the virgin compression line. So I have two change in void ratios I need to calculate. I have the change in void ratio from the over-consolidated portion, and I have the change in void ratio from my normally consolidated portion. So the change in void ratio from my over-consolidated portion is computed with that portion of the equation, and the change in void ratio from my normally consolidated portion is computed with this equation. If I combine them, then I get this equation right here, which allows me to compute the settlement of the soil. And this case is what I call case 3. The soil was over-consolidated, but now it becomes normally consolidated after the application of my induced stress. So that's all we're going to review for consolidation settlement. Now what I want to do is jump into introducing you to a new method that you've probably never heard of. Yanbu was a famous geotechnical engineer, and he was a genius, and he came up with lots of interesting and very fundamentally and mechanically sound methods for calculating resistances for foundation design, and also deformations due to applied stresses in the soil. And I'm going to introduce you to a method that he developed for calculating settlements in soils. Now, as by way of introduction, one of the greatest disadvantages of the approach that we just talked about is that everything I talked about with primary consolidation settlement applies only to clays and to silts. You treat sands completely differently. So you have to distinguish between whether you have a sand or a clay. There's sand-like behavior and there's clay-like behavior. Sands, you're going to calculate elastic settlements. Clays, you're going to calculate primary and secondary consolidation settlements. And they're two completely different methods. But in the real world, everything is not just clean sand and pure clay. There's always transitional soils. In fact, you're more likely to encounter transitional soil. And by transitional soil, I mean like a silty sand or a clayey sand or a sandy clay, a soil that is a mixture of both sand and fine-grained material. Very common in the real world. And those methods are not developed to handle those types of soils. So the Yanbu tangent modulus approach, the tangent modulus approach is a convenient way that can handle all soils, whether it's clean sands, whether it's pure clay, whether it's a silty sand, whether it is a clayey sand, and everything in between. And for that reason, it's referred to as a universal model, meaning no more elastic settlement, no more primary consolidation settlement, nothing yet like that. You compute settlement the same for all soil types. And you're going to do that using a single framework. And for this reason, I love this method. It's very simple. And to be honest, I'm surprised that it's not used more frequently in engineering design. When I was a consultant about 12, 13, 14 years ago, I was a consultant working on the Sacramento Levee Improvement Project, a massive multi-billion-dollar geotechnical design project, and we exclusively used the Yanbu tangent modulus approach to calculate the settlements on that project. And I suspect strongly that it would get more use if more engineers were taught about it or learned about it. And so that's one of the reasons I wanted to introduce it to you in this lesson. So let's dive in and learn a little bit. This method was introduced in the 1960s from a few key papers that you can Google or go to Google Scholar and you can find them. But the bulk of this lesson comes from a basic textbook written by a famous modern geotechnical engineer, Dr. Bengt Fellenius. I had the pleasure of meeting Dr. Fellenius once many years ago at a lecture he gave up in Seattle, and he's a very knowledgeable engineer and a very nice man. The book, I say here, it was updated in 2015. That's actually not true. It was actually updated in 2020. I just checked his website, and so that's the most recent version of the textbook. One of the things I love about Dr. Fellenius is he really doesn't care where his materials are published. And if you publish these materials in academic journals, it's great for academics, but the problem is for folks who are out in industry, unless you have a subscription to that journal, it's difficult to obtain the journal papers unless the author pays an open source or an open access fee, which can be several thousands of dollars. And so few authors are willing to pay that fee. Professor or Dr. Fellenius just has a website, fellenius.net. And if you go to the section on his website called Papers, he has over 400 technical papers that he just publishes himself and he puts on his own website. And he shares for free with the public. And so, you know, as a student, usually you're gouged for the textbooks that you have to purchase for school. Well, folks, here is a free textbook. You can see that the address to find that. The best thing to do is just go to fellenius.net/papers and then look for the Foundation Design textbook. Let me show you what that looks like. Here's fellenius.net/papers. Right now, it's publication 401. It's called the Red Book. A lot of people refer to it as the Red Book. If you click on it, here it is in electronic form. You can see why they call it the Red Book, because the cover is nice and red. Everything I'm talking about on the Yanbu method comes from Chapter 3 of this book. And for my students, that's going to be your assigned reading this week, is to read Chapter 3 of that book. It's about 26 pages, and it's pretty technical. So read it carefully, read it slowly, and if you have questions, note them down, and I'll be happy to respond to them. And basically, the Yanbu method is a simple function that uses two parameters. Every soil layer has to have a stress exponent, which we're going to call J, and then it has to have a modulus. So this is like any modulus you're used to, elastic modulus, or in this case it would be constrained modulus because the soil is confined by all of its neighboring soil. And so this M is a representation of like a constrained modulus in the soil. So here's the fundamental approach. This tangent modulus approach is fundamentally based on this parameter M sub t, which is the tangent modulus. And the tangent modulus comes straight from the consolidation curve. It's just equal to the change in stress divided by the change in strain. Now this is a little wacky because you guys are used to thinking of the consolidation curve with the stress on the x-axis and strain on the y-axis. And I'm telling you, with this approach, it's backwards. In this case, stress is on the y-axis and strain is on the x-axis. Okay, so it's just the slope. It's the slope of the inverted consolidation curve, where stress is the y-axis and strain is the x-axis. That's going to give you your tangent modulus, m sub t. By the way, we've talked in the past that the modulus of compressibility is equal to m sub v, and it's just equal to 1 over m sub v, where m sub v is just equal to the change in strain over the change in stress. And that's a popular term for conventional consolidation theory. That's the link between this tangent modulus approach and conventional consolidation theory. So let's dive in and look at a couple of these things. So there's that m, that's the modulus number for the soil. And there's two types. There's the modulus for the normally consolidated, but there's m sub r for recompression or over-consolidated soil. So over-consolidated soil has a different modulus than normally consolidated soil. Here's the J that we talked about, and again, that's the stress exponent that we'll introduce to you a little bit later. Sigma prime is, as you expected, the effective stress that's affecting that soil layer at depth, and sigma sub r, this is a reference stress, which for all practical purposes is equal to 100 kPa, which is basically just atmospheric pressure. Okay, so, whoops. Yeah, that m sub v, like we said, that's the coefficient of volume change, and that equals the change in strain of the soil divided by the change in stress. Okay, so first things first, let's talk about applying the Yanbu method to cohesionless soils. The whole name of the game with the Yanbu method is we want to calculate a strain. If I know the strain of the soil, I can say that settlement just equals strain times the thickness of that sublayer. So I need to come up with a strain for each sublayer in my soil. Here's how we're going to do it. This equation is the governing equation for cohesionless soil. Now, for cohesionless soil, the stress exponent J is always going to be larger than 0. Okay, it's going to be between 0 and 1. Okay, and if I have a value of 1 for J, that's going to imply that my soil is perfectly linear elastic. My soil is a linear elastic material. And that would be appropriate if I was dealing with a very, very dense soil like glacial till or rock. Something that was really, really over-consolidated or just solid. So if I have something that's completely solid and hard, I'm going to say that J equals 1, and we're going to assume linear elastic material. This is how we can use this framework to represent elastic settlement, if we just say J equals 1. Now, what if I have a soil that is non-elastic, that is plastic? So say I have a silty sand or a clayey sand. Well, in that case, J is going to be less than 1 but greater than 0. If you have no clue what J should be, then just using 0.5 is a great guess. And what about M? we need to come up with a modulus for our soil. Well, the best way to get the modulus is to measure it. Now, a common assumption that engineers make regarding settlement of cohesionless soils is that the settlement is due to linear elastic deformation, or elastic deformation of the soil particles. But rather than applying that the empirical or theoretical elastic settlement methods that we learned in 341, we're just going to use the Yanbu approach. So we're just going to use this basic assumption where the strain is equal to the change in effective stress. This is my induced stress that I can get from elastic induced stress methods, or I can get from finite element. And E is my Young's modulus. But according to Fellenius's terminology, he uses D for constrained modulus, and it's actually more appropriate to use constrained modulus instead of Young's modulus, because the soil is confined horizontally. It can strain in the vertical direction, but it has a difficult time straining in the horizontal direction. And so using that constrained modulus is considered a little more appropriate for these elastic methods. So just using equations or mechanics, I can calculate what the modulus is if I can come up with an estimate of the elastic or the constrained modulus. So I'm going to throw that modulus in there. I'm going to throw my estimate of the stress exponent J in there. And now I have all of my stresses in here. My reference stress of atmospheric pressure, my induced stress from my elastic methods, my effective stress of the soil as is in the ground, and right there again is my induced stress from my elastic methods. So that's a way I can calculate the modulus, assuming, of course, linear elastic methods. Now, if you don't want to assume linear elastic settlement for the sand and you want to account that there may be some consolidation settlement in there, then what you need to do is a consolidation test with the soil, and you need to actually compute your own M value at your target stress from the resulting test data. So you actually have to measure that M from the test as opposed to just approximating it from a linear method. But guess what? Retrieving cohesionless soil samples for undisturbed testing in the lab is really, really hard to do. So Fellenius recommends two possible approaches for getting M for cohesionless soils. So the first approach is to do a plate load test. Go out to the cohesionless soil in the field and you load the soil up with a plate. Now, some of you are probably thinking, what in the world is a plate load test? A plate load test looks something like this. Let me draw the ground surface here. So what I have here is just a block of soil in the field, okay? This is soil in the field. And a plate load test basically says you load a circular, sometimes a square plate on the ground, and then you apply a uniform stress to the plate. And then you measure the strain that results from it. And as you change the stress, you can measure the elastic strain. And so you get these plots that look like this, where I have change in load on the y-axis and I have the resulting movement of the plate on the x-axis. And for different diameters of plates, you can see that I can get different curves. If I normalize the load to the area of the plate, then I get stress. So all of those curves then fall right on top of one another, basically. So if I plot stress versus movement normalized to the width or the strain, then I can develop then the M from this curve. A second approach that Fellenius recommends is just to rely upon empirical correlations to estimate M from the field. So there's a handy relationship that he presents from a researcher called Massarch, published in 1994, which correlates the M modulus to uncorrected tip resistance from a CPT. So in order to use this equation, you have the tip resistance from the CPT, you have this A value, which is an empirical modulus modifier, depends on the soil type. So it's a function of the soil behavior type, or the soil type of the soil, and we'll get to that in a minute. We have the reference stress again, which is 100 kPa. We have the effective vertical stress of the soil. We have K naught, which is the at-rest earth pressure coefficient, which we can approximate using this equation right here, very common in geotechnical engineering. Using this equation, I can calculate the modulus, or approximate the modulus, with every little incremental depth in my CPT. So I could come up with a modulus value for every 2 centimeter thick layer in my soil profile, which is extremely powerful. Well, what do I mean by that? I'll show you in a minute. First, there's a table summarized in the Fellenius textbook from the Massarch paper, updated in 1997. So you can see for different soil types, he has different modifiers of A. And so you can basically just set up a macro, or you can set up a reference table in Excel, and depending on the soil behavior type, you can have it automatically grab a modulus modifier, depending on what your CPT is. What that looks like then is if I have a CPT profile that looks maybe something like this, and so I know I have a zone of clay, I have a zone of silt, and I have a zone of sand down here. I can, in a spreadsheet that gives me all of these different QT values, I can develop a series of moduli with depth for my CPT. Now, notice that the measured tip resistance is going to be very noisy. CPT data can be quite noisy, really jagged. So it's very common to do what we call filtering, where it's basically just averaging. And so you can see this line just kind of follows the average trends all the way down with depth in the CPT. And then using those averaged or filtered QT values is what we can use then to get our modulus. So for your homework assignment, this is actually something that you're going to be able to do, is calculate modulus with depth in your CPT spreadsheet. Now, that was cohesionless soil with the modulus A, or modulus M, and a stress exponent J. You can throw them into that strain equation and compute strain for your soil layer. But what if I have cohesive soils and I don't have cohesionless soils? It gets even easier with cohesive soils. If I have a cohesive soil, then J is equal to 0. J is going to be equal to 0. And if J is equal to 0, then what's going to happen is we're going to calculate strains according to these equations here. If I have a case 1 normally consolidated soil, I'm just going to use that equation right there. By the way, we're sigma 1. This is my induced stress, or my initial stress plus my induced stress. It's the stress after I've applied my new stress. That's what sigma 1 means in this case. For over-consolidated soil, it's the same as before, but notice the only difference is I'm using the reconsolidated modulus, M sub r. And then for over-consolidated soils turned normally consolidated, the case 3 soils, I'm going to use this equation down here, where I have to estimate what my pre-consolidation stress is, and I have my normally consolidated modulus and my reconsolidated modulus. Okay, simple, piece of cake. Now, what about modulus? We can directly relate the modulus to the consolidated parameters that you're already familiar with, C sub C and C sub R. So how do we do that? Using these equations right here. So the normally consolidated modulus is just going to equal ln of 10 times 1 plus E naught divided by C sub C. That's going to equal ln of 10 divided by C sub C prime, where that would be the slope of the virgin compression line in strain versus log of stress space. And then M sub R, same thing, but now we just have C sub R. So that's simply equal to the ln of 10 divided by C sub R prime. Piece of cake. So, you know, you can use your pick. If you want to go back and use the traditional Terzaghi method with consolidation curves, go for it. Or if you want to just convert those C sub R and C sub C values to moduli and throw them into the Yanbu method, you can do that too. The cool thing is you're going to compute the exact same answer either way. They're going to give you the same numbers. Okay, I've been referring to this for some time. This is a table pulled right out of the Fellenius text in Chapter 3. Very useful table. That shows a lot of different soil types with a typical range of modulus number. Again, I would not just pull a modulus number from this range. I would actually measure it in the field or the lab, or I would calculate it with a correlation. But the numbers you calculate, you can come to this table and check just to make sure that they fall within the range you'd expect them to. But what you're going to use this table for more commonly is the stress exponent. So again, notice everything that's clays or fine-grained, it's J equals 0. Everything that's very dense or hard, J equals 1. And then everything in between, very simple assumption, you can just assume J equals 0.5. Now, you can sharpen that pencil if you want to and adjust it. J, you know, the softer the material, the closer you're going to get to 0. So you can have J equals 0.3, J equals 0.2, J equals 0.4. The stiffer the material, the closer you're going to get to J equals 1. So, you know, feel free to adjust those ranges as you see fit. Now, let's talk about the pre-consolidation pressure with the Yanbu method. This is, in my opinion, one of the most attractive features of the Yanbu method because it allows us to identify the pre-consolidation pressure even for moderately disturbed soil samples. So I talked about how the consolidation curves are commonly flattened due to soil disturbance when we plot the traditional consolidation curves in strain or void ratio versus log of stress space. But if we instead plot the incremental conventional tangent modulus versus the average confining stress for a consolidation test, what we're going to find is that the low point right before, the low point in that curve, the low point corresponds to the pre-consolidation pressure. So it's going to look something like this. So here's what you're used to seeing from Terzaghi's work, where we have the traditional consolidation curve. You can see it's very flat. You know, we can do the Casa Grande method, and the pre-consolidation stress is going to be somewhere around there. but it's going to be more difficult. If I do the Yanbu tangent modulus approach, that's shown here on the right, the pre-consolidation stress always corresponds to the low part of the curve. And so that's going to be the pre-consolidation stress there. Now, let's go ahead and let's, I want to show you an example. This is going to be kind of fun. I've never done this before, but on your homework, I give you a set of consolidation test data, and I'm going to ask you to plot the constrained modulus or the tangent modulus and to find the pre-consolidation stress. So I want to show you how to do that. So this could be any sort of data that you get from a consolidation test, where we have P prime, that's our mean stress in the soil, which we're assuming is the essentially equivalent to the effective stress of the soil. And so you could see how if we were to plot that, well, see, so I've got mean stress, log of mean stress. Here's the height of the sample measured from the odometer. So the sample itself was originally, let's see, 24.618 millimeters plus 0.782 millimeters, 25.4. So H naught equals 25.4 millimeters. So that's the original height of our soil sample. So if I wanted to, and if you were interested in seeing it, I could plot the traditional consolidation curve. Let's go and select our data. For our x values, we're going to do the log of, actually, let's do this. Let's do P, but we're just going to plot it on a log scale. And Y, we're going to plot void ratio. So, you know, it looks goofy right now, but once we format this axis and we plot it on a log scale, it looks more like something that you guys are used to seeing. That's a traditional consolidation curve right there. Okay, let's compute the strain in the soil. Now, the strain in the soil is simply going to equal the change in height divided by the initial thickness of the soil, which is 25.4 millimeters. So change in height divided by initial height, that's strain. So there we go. Now we have all that strain plotted. I'm going to go to a whiteboard here for a second to show you something. Now, if I were to plot that looks like this, where now I have strain on the x-axis and I have stress, I'll just put it P prime on the y-axis. For all of my points, I would get a curve that would look something like this. And I'll show you. Let's go ahead and make that plot. Let's add a new plot, and we're going to make it a scatter plot. And let's select the data, and on the x-axis we want to do strain, which I know seems backwards to you, but just trust me. Whoops, nope, I did that wrong. X-axis, I want it to be strain, and on the y-axis, I want it to be mean stress. but I only want to plot, I don't want to plot the rebound portion. I just want to plot it right up to where we rebound the soil. There we go. Okay, so in this particular plot right here, here's a screen capture. I have P prime on this axis, and then I have strain on that axis. So you can see that as I increase my strain, that corresponds to an increase in the mean stress in the soil. Now, you're going to recall that the tangent modulus is equal to the change in stress over the change in strain, or change in P prime over the change in strain. What that basically means is the derivative of this curve. So what I want to do when I plot the data in this way is I want to fit a function to it, and then I want to calculate the derivative of that function. And that's going to give me the equation for the tangent modulus. Very cool stuff. So let's show you how we're going to do that. So Excel is a very useful tool. I'm going to click on a point. I'm going to add a trend line. Let's display the equation on the chart. And what I want is a line that fits my data points as best as possible. So if let's go back. There we go. Okay, so if I pick a linear trend line, you can see that my R squared looks good, but you can see that line does not go through all my points. So that's a bad fit. If I did an exponential function, it's a little better fit, but you can see, I'm going to delete that right there. You can see that the that line still doesn't go through all of my points. If I do logarithmic, it's not a good trend line. I don't get good data on that line. So more commonly, you're going to want to use a polynomial. So here's a second order polynomial, and you see that we're getting closer. We're almost through all those points. If I go to third order, oh man, that line really goes through all of those points really, really nicely. So I could stick with that. If I wanted to, I could go fourth order. I don't see a lot of change from the third order. So I'm going to go back to the third order. And that's the equation. And check out that R squared, 0.9998. It's almost a perfect fit with the data from my, my plot. Okay, so now there's my equation right there, where again, y is essentially P prime. So we're saying P prime equals 139,482 times strain cubed minus 34257 times strain squared plus, and you can see what I'm doing here, right? I'm running out of space. Okay, so m sub t is going to equal change in P prime over change in strain. So all I need to do is take the derivative of that function right there, where x is strain and y is P prime. So d P prime is simply equal to 139,482 times 3 times strain squared. So I'm just taking the derivative of a polynomial. That's all I'm doing here. Minus 34257 times 2 times strain to the 1 power plus 5014.6, and all of this times d strain. So that's my function. That's the function that I want to use. So let's do something magical here. Let's go ahead and calculate that function and show you what that bad boy is going to look like. So what I want, first of all, is my strain. And let's just copy all the strain values that I had down to the point where I rebounded in my testing. I'll paste those numerically. So those are my strain values. Let's calculate my P prime values, and I believe those were in kPa. And that's equal to these values right here. Okay, now let's write my function for m sub t. And that's simply going to, by the way, that's in units of kPa as well, just in case you're wondering. So that's going to equal this function that I just came up with, 139,482 times 3 times strain cubed, or squared, excuse me, minus 34257 times 2 times strain to the 1 power plus 5014.6. So that is my tangent modulus at these corresponding mean stresses. So now if I were to plot on this, let's add a series for my tangent modulus, where x is going to be strain, y is going to be the tangent modulus, whoops, let's just do a new plot. That way we're not going to be so messy. But this time, if I want to find the pre-consolidation stress, I'm going to plot tangent modulus versus effective stress or mean stress. So let's plot a scatter plot with a fit function to it. On this instance, for my x, I'm going to use mean stress. And for y, I'm going to use tangent modulus. And I hit OK. There it is, folks. Let me screenshot this. You see how that curve bottoms out right there? Where that curve bottoms out, that is my pre-consolidation stress. So for this particular plot, it looks like it's about equal to 100 and let's see if that's 100. It's less than 150. I'd say maybe 125, maybe 120 kPa. But that's how we can automate finding the pre-consolidation stress inside of a spreadsheet. You could go this further, and if you wanted to take the derivative of this function now and fit a curve to that and then find the derivative of that, the pre-consolidation stress would occur where the derivative of this tangent modulus function equals 0. That would be the minimum of that curve. And so you could find the pre-consolidation stress with precision for this particular soil depth. So a very handy approach, and you're going to want to be able to do that on your homework assignment when you need to compute the pre-consolidation stress using the Yanbu tangent modulus approach. All right. I hope this was useful to all of you guys. I look forward to your comments. I look forward to your questions. And hopefully you'll find a lot of satisfaction in using the Yanbu method in your practice. I certainly know that I've had a lot of satisfaction with it in my practice. So thanks for your attention, and thanks for allowing me to share this information with you. Stay safe out there, and have a wonderful day.